we considered one converter which connects a DC side to another DC side. Especially on the side B, we considered voltage. We call it grid voltage, and we controlled power. So we controlled power going from side A to side B. This is a situation that you have either a power grid or a grid, a microgrid on the B side, on the right side here, or for instance you have a battery, you want to charge your battery. So again, the battery supplies a voltage. So that is the case that we can, normally they call it grid feeding. So you feed power to the grid, okay? So this mode of operation is called grid feeding. There are two other names for the same thing, and these names are slightly different, but overall in the same category. It's grid following, yeah, but I'm going to say that later because we haven't got to that point. And grid supporting, right? So all these three basically assume that there is a grid. So there is a grid, you just feed to the grid, or you follow the grid and support the grid. If the grid kind of goes up and down, has some fluctuations, you support the grid, either inertia or static support, droop support, or both of them, right? So terminology is not very accurate, so I cannot say what is the difference between grid following and grid supportive, but the concept is clear. The assumption is there is a grid that supplies a voltage, and now you are feeding power to that grid, either without support or with some support. That's this. Now, we would like to extend this concept to the case that there may not be a grid. And we want these converters to form or to generate a grid themselves. And that the concept of grid forming converters come up. So now I start slowly to get to that case. Now, first we go to the extreme case on the other side, which is no grid absolutely, and there is only one load. And then we try to go to the middle point, which is basically once we want to form a grid. So this converter is here. This is load voltage control. And our objective now is not to feed power. Our objective is to control the voltage across this load. This load is supposed to receive a given amount of voltage, let's say 400 volt, 300 volt, whatever, and then we want to make sure that this load receives that voltage. So control the output voltage VG at or closely around the desired value of capital VG. So capital VG is for the desired value, lowercase vg is for the actual value. And obviously always in the feedback control, this is one of our main objectives. We would like to attain this objective robustly with respect to all parameters that you can imagine in this system. In this system, these are all the parameters that you can imagine. And in terms of disturbances, you can look at, for instance, when load suddenly changes, that is a disturbance. So another load switches in or switches off. So that's variation of this load here. We know we want to have a response which is quick and smooth. And obviously this is a condition that we always need to satisfy because we are working with power electronics, so we need to limit the current. Okay. So transfer function of this system, we have a capacitor here. We need to put a capacitor now here because this capacitor absorbs the switching noise of this inductor current in it and makes the voltage more smooth. If you don't put this capacitor here, the voltage across this load will have large switching ripples. So capacitor really absorbs those switching ripples, and now you have a nice voltage across the load. So whenever it's a voltage control, you need to put a capacitor there in converters. Okay, So this is a second order system. You have R, you have L, and then you have C or C1. This C, we'll talk about details of this later. So from this side now we are talking. This is a second order system, and then transfer function of this system you can easily derive. That will be a second order transfer function. And the modeling of this system is like this. So M into Vc, that gives you V. M into Vc, that gives you this V. And then V minus this V divided by this impedance give you I. And then I multiply into this impedance give you V. So that's basically this diagram says. V minus Vg divided by this impedance is I multiply into that impedance, that gives you Vg. So either block diagram or equation. This equation and this block diagram are equivalent. So one thing we realize is that this system, if you look at the poles of this system, again it has two poles, not one pole, it has two poles. And generally speaking, at least in unloaded condition, not in loaded condition, in unloaded condition, these two poles are very close to the imaginary axis. If R is 0, which we know it's very small, and G is also 0, which is unloaded situation, the two poles are exactly on the imaginary axis. So open loop system is marginally, you can say, unstable, or it's not well respond. Okay, so what do we do in control? In control, what we do, if we want to go with that optimal control approach, is that we look at this system. It has two state variables. One is the current, and then one is this voltage. So we take this current, multiply into one gain. We take this voltage, multiply into one gain. And then we want to remove this state error, so we add one integrator. And the output of the integrator will be another state variable. Multiply that into K1, and then add them all together. So this is the standard form of a full state feedback. And this VFF, feed forward, is for startup. For the startup and also for current limiting. You remember, both of them, you can merge them together. Okay. So these are the equations of the system. Now x1 dot for this one is E, which is x2 minus Vg. x2 dot comes from this equation here, and x3 dot comes from this equation. So you need to be able to write down the state space equations if you want to go with this approach every time. So if you are not good at it, please try to practice on your own a little bit. Deriving these state space equations is very important in order to be able to design optimal controllers. So please try on your own to derive these equations and make sure that you can do it. Okay, and modulation index is negative K1 x1, negative K2 x2, negative K3 x3, plus the feed forward term. So negative Kx plus VFF. Now you see both the state space equation and the control equation has some additional terms. The additional term here is this one. And what I mean by additional term, comparing to the LQR, or regulation problem. And in the control is this one. The way to remove them is to apply this d over dt operator to both sides of this equation and state space equations. So if you apply this to the state space equations, you will get these three, right? Z1 is x1 dot, Z2 is x2 dot, Z3 is x3 dot, right? And especially Z1, which is x1 dot, is the tracking error. This is really important about this approach. So this transformed state variable represents or is exactly equal to the tracking error. So the cost function that we can minimize is Q into a square of error, Q2 into a square of Z2, Q3 into a square of Z3, and N squared. N is derivative of modulation index, and Z2 is derivative of the voltage, and Z3 is derivative of the current. So basically this approach, what it does to remove the constant values, applies the derivative, and now minimizes the derivative terms, the energy of the derivative terms. Okay, so matrix A is known, matrix B, and matrix Q, and then you can apply, go to MATLAB and apply LQR. This example I think we will check on what I have. No, the next example I will do the simulation, but anyway. So let's carry out the design here. The parameters I consider pretty much the same numbers that we had before. 400 volt on the A side, 300 volts on the load side, and these are the load resistance. That means a power of 1000 watts or 1 kilowatt. The inductance is 5 millihenry, capacitance is 400 microfarad, and that parasitic resistance is 30 milliohm, and switching frequency 4 kilohertz. Now if you run the LQR, LQT or LQR, and I will run it for the next example for you here so you will see, and then once you increase Q, you will see all three poles move, two of them here complex and one of them real. Then let's say at some point you stop Q and increase Q2, then you will see this behavior. This go now a little bit more damping, they go down, but the other one starts coming back. And now once you apply Q3, you will get more damping, and this pole also will move to the left. So you would like to have these two poles to have sufficient damping, these two complex poles, and this real pole obviously doesn't have a damping problem, and all three poles you want them to be sufficiently distanced from the imaginary axis, so your transient response is sufficiently fast. For instance, here they are at about negative 1300, right? So you will get responses under 1 millisecond time constant, roughly speaking. Okay. This simulation shows you some of the results. So this is the starting, it's very smooth. And I think the full load is connected. Yeah, the load is connected. Yeah, full load, I believe, because the current goes to 3.3. And then at this point, we change the set point of the voltage from 300 to 320. We want to see how controller can apply or can follow the commands. If I want to change the voltage from 300 to 320, does it follow? And then you will see, yes, it clearly follows, with almost the same time constant that you had expected. And the transients and oscillations are great. You don't have any extra oscillations here. And then come back to 300. And here, let me see what kind of disturbances I have applied. At this point it's clear because I have shown I have applied a disturbance on the left side. The voltage drops from 400 to 370 and then back again to 400, and you see almost no change, a little glitch, and that's it. Very robust. At this point, however, I added one more resistance in parallel to the output. I think equal amount of resistance. So that means now the power is increased. When the power is increased, the current is also increased, but the voltage remains exactly at 300. Then back. So that responds to load increase, load decrease. Both of them are tested here. Load increase, load decrease. This point is where I applied a large load or a small resistance at the output. So the current becomes significantly large, like 13.3. Remember, the rated current is 3.3. The rated load for 1 kilowatt is 3.3. Now it goes to 13.3, and then I remove that load, it comes back. And the voltage shows some transients, but it eventually goes back again to 300. So this seems like a very nice performance, except one big problem. Can anybody say? We did not satisfy one of the requirements, and that requirement is very important. Yes. Yeah, because we never put that there, right? We never put it there. So this approach is very well, but it is not able to limit the current, and it's very important. Current limiting, we cannot really ignore it. So next section, we are going to incorporate the current limiting into this control structure. Uh-huh. Uh-huh. Right, right. That's right. Uh-huh. Mm-hmm. That's a very good question. However, my answer is, when you say this converter is supposed to operate at the rated 1 kilowatt, that's the rated value. It can go from 0 to 1 kilowatt, and even maybe slightly above 1 kilowatt, depending how much you have, how much room you have given to your switches and everything, because switches really determine the relay rating, right? So in this kind of applications, this is the common practice. You design it for the rated value, because we don't have any other really. If we don't do that, what should we do? We should start from somewhere. If you want to have a deep study, you need to come back later and say, okay, now if it's not rated load, what happens? Either show it by simulation. If simulation shows that it works, that's fine. Or if simulation doesn't work, you know that there is a problem. You need to go and fix that problem. But rated load is basically the approach. Mm-hmm. Yeah, these are any ideas we can always do, but keep in mind that it will be one sensor added and possibly one point of failure and one more point of sensitivity and things like that. And that current in practice could also be a noisy current. So these things should be all considered. I haven't seen in these applications that people use the load current as feedback. Okay, so like we said, this approach has this problem. We need to fix that problem. The way to fix that problem is this. We actually establish a current loop, because whenever you want to limit the current, you have to have a current loop. So if you look at this one, is a current loop, because there is a reference of current and there is the actual value of current, and then you put one integrator here, and then this gives you one additional state variable, and now close a full state feedback here. So that will be K1, K2 and K3. So now the feedback loop is closed on current. If I saturate this reference or limit this reference, I can limit the current. Okay? So I do that. Now the question is, where do I get the reference of the current? The reference of the current, one idea is to get it this way. Get I star equals capital I, which is the rated current, plus K0 into capital VG minus the actual VG. Or in equation is basically this, which is a Drup form, right? So it says what? It says when VG is equal to capital VG, I star is equal to I. So at the full load condition, when the current is I, capital I, the voltage is also equal to capital VG, the actual number that we want. But as the current goes up, the voltage will go down, or vice versa. As the current goes down, the voltage goes up. And the level of that change in the voltage you can control by this K0. So you can say, I would not mind that my voltage changes plus minus 2% or 3%, which is normally acceptable ranges, 2, 3, 4, 5%, depending on the application. So I would allow the voltage to change plus minus 5%, and then from that change I generate the reference for the current here. So this K0 basically the design of K0 comes from how much you want your voltage to change, right? So basically is coming from this equation. If you want, for instance, 2%, if you want 2%, it will be I divided by 0.02 VG. 5%, 0.05 VG, things like that. So now this is designed based on that level of voltage. Now this is known. Let's write down the equations of this entire system. And this does not add a new state variable, remember. Still we have 3 state variables. Let's write down the equations, the state equations of this system. Wanted to open this also. See what we can do. So then I write down the state equations for this system, and this is the state feedback law. And still you see we have a couple of numbers, like constant numbers here, like this one and this one. We don't have much here. Then you need to apply again the derivative to this one, and then you will get these 3 equations. And each z1, zi, is equal to derivative of xi, and this n is basically derivative of modulation index. So you can minimize this cost function. Tracking error directly is in the cost function, and derivative of voltage and derivative of current and derivative of the modulation index. All of them are in the cost function. So you run this LQR problem and then you find K. This example shows the procedure for the same numbers that we had. This is the graph of the closed loop poles or closed loop eigenvalues when you increase Q and then increase Q2 and increase Q3, just to show you the whole picture. You don't even have to use Q2 and Q3, but if you used it, you can refine your response. Here you are fine-tuning your response by increasing the damping a little bit and things like that. Now the rated current is 3.33, and let's say we want to make sure the current is limited at plus minus 8 amperes. I think the current limits is plus minus 8 amperes. And here I think I ran similar situation that we had before. Okay, so this is the starting transient when the output voltage is 0, and then it takes some time to go up. During this time that is going up, and if you look at that, it linearly goes up because the current is limited. So it's exactly 8 amperes is going to the capacitor, and then linearly the voltage keeps going up. Once it reaches there, the current comes back to the rated 3.3. Here we applied a set point change from 300 to 290, and this is the transient that you can see. So this figure basically is the same. It's a zoomed version of the same thing. And this is the current, and these points, I believe, let's see what happens. The disturbances, a couple of disturbances are applied on VC, for instance. I think at 0.7 to DC voltage disturbances at 0.7 to 0.07 and 0.8 DC voltage disturbances. These two, basically no impact. The voltage remains and the current is also the same. And then at this point load increases. So let's say you increase the load, again you increase it, and again you increase it. So keep increasing it. So once you increase it, you realize the voltage drops. See? And then you increase it again, it drops. Now you increase it such that it goes to the current limiting mode, right? So when it goes to current limiting mode, it cannot feed the current that the load requires to keep the voltage. So the voltage drops more. So in that extreme situation, when the load is large but the converter is not allowed to provide that current, the voltage significantly drops, is this one. And this is even more significant scenario. The current still is limited and the voltage drops more. Okay. And here goes back to normal, I believe. It goes back to normal again. So all these additional loads are removed, it goes back to normal. So really extreme situations are simulated to show that it works. And what happens here at 0.38 to a deep voltage sag at 0.38. And deep voltage sag. I think that I meant a short circuit almost at the output, or a very large amount of load at the output, because voltage sag doesn't mean anything here. It's not grid connected. Okay. So it's basically this case here is an extreme or a stronger case of this one. So the huge amount of load, or you can say almost a short circuit at the output terminals happens. So the voltage drops all the way to 100 volts, but the current still is limited at 8 amperes. And then it's removed. When it's removed, again, for some time, it takes for the voltage to build up linearly, and the current is still 8 amperes. Once it reaches that voltage, the current goes back to 3.3. Okay. So this simulation, as you saw, my computer didn't open the Simulink file because it says it's generated by a newer version. I don't know what happened because the others did not have this problem. But at least the code I have here, let me run the code, part of the code for this design. So the simulation may not run, but let me run the code for you, the design code. So this code, let me explain the code just a couple of minutes. For this design, K0 is 1, and A, matrix A and B, you need to provide A and B. And then you have Q1, Q2, Q3. Always we start with Q1, so you put Q2 and Q3 0. And then you change Q1 in a loop, and every time you run the LQR, and then you plot the eigenvalues. And you hold on, so you stay on the same graph. Let me run this part only. See. So when you increase Q1 from 10 to the power of 0 to 10 to the power of 3, and Q2 and Q3 are 0. These are the poles of the closed loop system. And then let me run the other part. This is when you increase Q2, and then finally when you increase Q3. I don't think we can run the Simulink. Let me see if it runs. Try at least. Yeah, it gives error, so it doesn't run. So it means that this file, the Simulink file, was generated with the MATLAB, which is newer than the MATLAB which is here. I made sure that all files are generated, but for some reason this is in. Okay. 2022. But for other ones we didn't have problem, right? So how come? Okay, later I will give it to you, sure. All right. So let me see if the other one, while we are teaching, at least try to open one of the other ones. All right, so now we are almost ready to go into grid forming converter controls. Yes. Yeah, you can stay there. You can stay there, no problem. You can put an integrator. Yes. Right, right. Yes, I think I will talk more about that as we go on a little bit. But one thing I realized, and I had one PhD student to really answer this question, whether it's better to put a integrator there or not. It's a simple question, but it was a PhD work. Even I can show you his dissertation and his papers. He published a couple of good journal papers. So the conclusion was that if we do not put an integrator and we'll allow the voltage to play around a little bit, like 2%, 3%, maybe 5% maximum, first of all, the design and everything is simpler. Secondly, and more importantly, is that the closed loop feedback system will have much more robustness and stability properties. So this system that you will allow the voltage to move up and down, it will be much more robust and stable in extreme cases. Yeah. And especially in grid connected mode and in inverters. So he discussed all DC, AC, single phase AC, three phase AC. That became a PhD work. But the core idea was, should I use an integrator there or no? but he answered the question for these different cases, and that became a PhD work. Right. K1, K2, K3. But K naught comes from, it's a Drup function. So basically, if you look at this equation, that means if you would allow this to drop whatever percent, then you know how much current changes. So you choose K0 according to that. It's a simple line, and then the slope of that line you choose. Oh yeah. Yes, first you choose K0 because we used K0 in the LQT, right? See, K0 is somewhere here in the equations. I don't know. Where is it? Was it there? Oh, here. There you go. K0 is here. Yeah. All right. So, grid forming converter control. So grid forming means that we want this converter to be able to form a grid, meaning that if grid is not available, the converter can provide or generate a voltage for the loads that are connected, and that voltage should be close to the voltage that a grid would provide. So if the grid is 120 volts, for instance, and now suddenly the grid is not available, the loads should still receive a voltage of 120 volts from the converters, right? Maybe slightly different, but close to that. And if it's connected to the grid, and now the grid is the main part that provides the voltage, they should still work. In other words, these converters, grid-forming converters, should be able to operate in both modes, grid connected and grid disconnected or islanded. So this is basically the statement of the problem. Here we have the situation that there are some loads and there may be a grid also, and this is the switch that connects to the grid, but there may be that this switch is not to make it a little shorter, that this switch may be open or may be closed. So it should operate in both modes, whether it's open or closed. That is the concept of grid forming. The extreme case that we just discussed was when the grid was not there. The other extreme case that we discussed yesterday was when this load was not there and this grid was connected completely. Or if the load is there and is connected to the grid, no problem, because the grid really provides the voltage. So the converter was not supposed to provide any voltage. So in grid feeding or grid following and even grid supportive, the converter is not responsible to provide a voltage. The best it can do is to support the voltage. But in grid forming, the converter is responsible to form or to provide a voltage when the grid is not there. And when the grid is there, it provides support, obviously, to the grid. So when the grid is connected, it's grid supportive. So you will see automatically provides support. All right. So I broke it down to two cases. Let me see how I proceeded. And we'll do that in DC and AC. In AC is more common, this concept, but in DC also we can talk, no problem. So still, because we want to have current limiting, so this current loop should be there. Remember, this always must be there. So power divided by the grid voltage, that is the current reference. So the reference power divided by grid voltage, that's the reference current. You limit that. And then that is the reference current, and subtract from the actual current, and then a feedback loop here. And in feedback loop here, this is an integrator, so it gives you one new state variable. Then you have another state variable here, right? That's the current. And then, okay. This K2 is a state variable of this one. So there is a state variable also coming from this one. Okay. Now, this approach here, which it will work for DC, but it may not work for AC, it says, I'm going to add a droop term here. So this is static droop support. And then I'm going to add an inertia term here. So inertia term, remember what it was? It was derivative. It was proportional to the derivative with negative sign. So derivative of the grid voltage with negative sign. And then there is another term here which you don't need to worry now, because this is basically for AC. But in order to complete the picture, I put it here. That's the synchronization term here. And this is the set point of the power. So it says this is basically a grid following or grid feeding, but it adds both the static support and the dynamic support to it without adding a capacitor. So that's one approach. So it's basically not necessarily providing voltage, but the fact that it brings this droop term here, it says, I will try to keep this voltage close to this one. Right? So in other words, there is a point in this controller that says, I will try, I do my best to keep that voltage close to this one. That's the concept of grid forming. So let's hope that this term, if we choose it sufficiently strong, it can do the work. So in DC, it works, no problem. Without a DC capacitor. Yeah, and these are the simulations here. For the simulations, if you look at this one, I have between 0 and 0.15 grid forming controller, between 0 and 15, and larger than 25 is standalone. Standalone means it's disconnected from the grid. So between here and all the way to here and here, it's disconnected from the grid. And then here to here is connected to the grid. So at the beginning, it starts disconnected from the grid. So it builds up the voltage linearly because it limits the current at 8 amperes. So it goes up. And once it reaches there, the current comes back to 3.3. Now, in the disconnected mode or islanded mode, load may increase. So here is the case that you increase the load. If you increase the load, the voltage goes down. Remember, this voltage drop is very small, 300 to 296, right? And then here, 0.1. I think that synchronization term I added. Don't worry about that. We'll come back to it. So that synchronization term, the job of that synchronization term here is this synchronization term. What it does, it basically, and we have this concept very much in AC. We discussed that in AC in more detail. It looks at this voltage and this voltage and the difference between the two voltages, and then brings the difference between the two to the feedback loop. And the feedback loop will push these two voltages close to each other, so now you can connect the grid switch. Okay. And then at this point, it's connected to the grid. So when you connect to the grid, right, this is the voltage on the grid side and voltage on the load side. They become equal. And then here, the voltage drops, no problem. And it provides support. Because the voltage drops, it provides support. The converter provides support. And then at this point, again, it's disconnected from the grid, and no problem, it goes back to the disconnected mode. So you will see in DC, it's not very challenging. The same supportive terms that we had, dynamic support and static support, if they are strong enough, they can provide a grid forming converter. However, the implementation is not it's not the only implementation. Here, the other implementation is this one. Either an actual capacitor or emulated capacitor. Let's say you want to emulate a capacitor, because capacitor provides inertia, right? In the just previous example, what we did, we differentiate the grid voltage. This is some people do. I personally don't like that approach. This approach of using a capacitor or emulated capacitor is more robust and more reasonable. Differentiation always is difficult to manage. So, but capacitor provides inertia, as we discussed in detail yesterday. So for inertia, we use a capacitor, but for the droop, we have to use the droop anyway, right? So that's the droop. And this is the synchronization term. And this is inertia. So basically this says for inertia you have two ways of implementing inertia. Either differentiate the grid voltage or use a capacitor. This one opened, okay. Good news. The other file opened. So, like I said, the capacitor could be emulated. This is emulated capacitor. Or if you have an actual capacitor, no problem. It's an actual. You can get inertia from actual capacitor if it's a two-stage converter. Okay, and examples and designs are done here. Pretty much the same responses. If you realize, tend to be smoother than the other one, but overall pretty much the same responses. So again, here I think from here to here is disconnected from the grid, and again here disconnected from the grid, and the other part is connected to the grid. It's connected to the grid. And then when disconnected from the grid, the disturbances that you can apply, you change the load. And when it's connected to the grid, the disturbances that you can apply, you can change the grid voltage. And you should get grid supportive function. So for instance, when the grid voltage drops here, the converter should provide more power or more current, which is true, you see. This is a grid supportive function. See if the example is 17. Yeah, that's it. Let's do this one.
When it is operating in islanded mode, it is forming the voltage.
Yes.
When it comes in the grid connected mode, is it operating as a voltage source or it is operating as a current source? The converter.
I have to, yeah, the answer to this question. I don't want to give a quick wrong answer. See, the converter, basically what the converter generates or provides is this voltage, right? Is this is the modulation index, or eventually this voltage. Right. So it's a voltage source, but it's controlled by the amount of current, something like that. I don't think it's a very accurate question. You know, the question is not very well posed to answer.
It will be very good
Right.
So this converter can act in both ways,
Mhm.
as a current control or voltage as a voltage source.
Right.
So it may not be significant here in case of PC,
Right.
but it will be, then we need to
Over
decide
there, yeah.
whether we are operating as a
That's
voltage source or we are operating
that's
as a
right.
current source.
That's right. Yeah. Over there, the question over there is better, can be better answered, but here not very much. Yeah. All right. So there is the oscilloscope. So we put separate oscilloscopes here. For instance, this is the current, this is the voltage. And these are the switches that use to change the load. So this is the voltage source converter. A capacitor is here, actual capacitor is here, and the power, the current source here. So it's just like a two-stage, but the first stage we are not concerned with the first stage now. So we model the first stage as a power source, basically. And then this is the current of the inductor, and this is the capacitor. Probably I have put a small resistor here, and this is the load and the voltage of the load, and then one switch here connected to grid, right? So that when you open that switch, it disconnects from the grid, and when you close it, it connects to the grid. Okay, so let me see what I can open. Looks like very slow, even opening an oscilloscope. Now it's open here. All right. This was already open. I don't know why it doesn't show on the oscilloscope. Oh, now it's showing. Has some delay. The inverter current. This is the converter current. This is the capacitor voltage, which builds up using the starting time. And this is the grid voltage or load voltage. And this is the grid voltage. So this is load voltage. At the beginning, it's not connected to the grid, so the converter builds the voltage up to 300. Then you have a load change because you see the current goes up. So you have a load change. And the voltage goes down. And then again, you, I don't know what happens, maybe synchronization is activated. And at this point 3, you connect to the grid. So the voltage of load and grid become equal, and at this point you drop the grid voltage. Okay. So the codes are also there, but it's a little time consuming to, let me see if I can open it quickly. Okay, quickly opened. So the design stage is always in these codes at the beginning, so you can see that. And then after the design is complete, it runs the simulation file and provides the results of the simulation file.
So the first it makes two metrics
Mhm.
using properly selecting this pool location,
Right,
and then it run the
simulation.
ACAR formula to get this K1 K2.
No, LQR get it. We never run Aker anymore.
Yeah, LQR. Sorry.
Right,
That is
LQR.
LQR to get this gains
Right,
K1 K2.
right, exactly.
But first we need to select the pole position where we want to.
What we do basically, we change them and roughly find a point that gives good damping and good speed. That's it. We don't select really the poles location. We just say, okay, these points here are good because they are 1,400 from the axis, so that means less than 1 millisecond time constant. And the damping is very good, less than more than 0.7. So why not? Let's go with this one, and then you run the simulation and this figure already. Okay, so let's see how much is left from this chapter. Okay, so let's talk about this PV in the next class. We'll get about 10 minutes break. Let's make the breaks a little shorter so I have more time to. Okay, 10 minutes.